purpose of neurons is to communicate. And in order to talk to their postsynaptic targets, neurons must fire action potentials. And the action potential is the most exciting 3 to 4 milliseconds of our lives. This is where the membrane potential of a neuron goes from about -70 to somewhere around +30, then back to -70, in fact a little below. We go even more hyperpolarized, and then we creep back up to rest. And each of those steps takes somewhere in the ballpark of a millisecond to depolarize from threshold to +30 or so, a millisecond to repolarize, and then we'll hang out 1 or maybe 2 milliseconds in the after hyperpolarization. So we're no longer dealing with just leak channels. Now we got to think about gated channels. And the big ones to consider would be voltage gated ion channels. We'll touch on ligand gated just a bit. They get the whole process started, but the action potential is driven by voltage gated ion channels. Then finally we'll discuss myelination and how that speeds up the propagation of action potentials. Alrighty, so that massive change in membrane potential that comes from just a little change in membrane potential, that's driven by voltage gated ion channels. Now this all probably starts somewhere around the dendrites. A neuron is going to get a bunch of input. If we're in the central nervous system, there's going to be a lot of synapses. That need to operate together because each synapse is very weak. They're all going to create just a little bit of depolarization out there in the dendrites. So that electrical activity is going to propagate, we'll say passively. In some cases that's true. There's also active propagation in the dendrites. But all those depolarizing currents are going to sum about in the cell body. And those charges are going to collect as they move randomly at the initial segment of the axon. Now, dendrites are actually bigger than axons, but the axon is where we're hanging out today. Now remember that initial segment, smaller than the cell body, so we're going to have a higher internal resistance. That's going to amplify the potential change. And we also have a whole bunch of sodium channels, in this case voltage-gated sodium channels. In order to kick off an action potential, we have to hit threshold potential. We have to depolarize enough to turn on the voltage-gated ion channels. So out here in the dendrites, these are ligand-gated. We need a neurotransmitter to bind, and that's what opens up the ion channel. The electrical events here in the dendrites find their way to the axon to activate voltage-gated ion channels. We'll start with sodium, then we'll move on to potassium, because that's what goes on in the action potential. So synaptic potentials from ligand-gated ion channels sum to activate voltage-gated ion channels in the axon. And now we're finally firing an action potential. The action potential is going to propagate down the axon because it's going to drive depolarization, and that's going to activate voltage-gated ion channels in the next segment, in the next segment, and the next segment. So this is self-propagating. Once it starts, it goes all the way down to the end, unless we have demyelination or something like that. There's going to be an increase in the permeability to sodium. That, of course, brings the membrane potential closer to sodium's reversal, somewhere in the ballpark of positive 56 millivolts. Of course, we're not going to make it all the way because we still have leak. We still have leak currents holding us around rest. So we'll get somewhere close, though. We'll be between 0 and 56, probably around 30 millivolts or so. The specific number doesn't matter, but we're going to go positive. Then we have an increase in potassium permeability, and that's going to drive repolarization. So the order of events here, first, this is our membrane potential. We're around minus 70 millivolts or so. The first thing we have to do is hit threshold. That's going to turn on our sodium channels. Once we hit that, we depolarize. That's step 2. That's caused by voltage-gated sodium channels. Then we repolarize. In fact, we after hyperpolarize and then come back. So steps 3 and 4, the repolarization and the after hyperpolarization, that's caused by voltage-gated potassium channels. So first sodium, then potassium. Sodium comes in, potassium leaves. Each of these steps, something like a millisecond or so. We allow a little more time for the after hyperpolarization. So just remember, it's somewhere in the ballpark of 3 to 4 milliseconds for this whole thing to complete. Now action potentials are all or none. That means we either fire one or we don't. If we hit threshold, we fire an action potential. If we don't hit threshold, we don't. So depending on how many synaptic currents we can sum together, we either fire or we don't. There's no half action potential. All or none. That depolarization is caused by our voltage-gated sodium channels. And they're exactly what they sound like. They're sodium channels, so they move sodium. When they open, membrane potential moves toward positive 56. They're voltage-gated as well. That means what determines their activation state is membrane potential. Did we depolarize? And I want you to notice here, depolarization turns them on and they cause depolarization. Now that's a positive feedback loop. So depolarization from the synapses turn on voltage-gated sodium channels. They're sodium channels, so they're going to depolarize us further. That depolarization turns on voltage-gated sodium channels, which depolarizes, which turns on voltage-gated sodium channels. So once we hit threshold, that's why this is all or none. All of the voltage-gated sodium channels will be activated. Because once one activates, we depolarize further. The odds of others activating increases until they all open up. And we're going to hit about the same peak every time we fire an action potential. The ion pore is made from the 5th and 6th transmembrane domains of each segment. So it's a single polypeptide chain that forms 4 different domains, and each of those have 6 transmembrane domains. In case you care, the 5th and the 6th are oriented into the middle. The reason that matters is because the 4th transmembrane domain is the voltage sensor. That's the activation gate. Notice 4 comes right before 5 and 6. So that means the 4th transmembrane domain is closely connected to the 5th and 6th. So when it moves, so does the 5th and 6th transmembrane domains. That 4th transmembrane domain has some positively charged amino acids that are going to respond to changes in membrane potential, just like last lecture. So when some positive charge comes in, that pushes on positively charged amino acids in the 4th transmembrane domain. The movement of those amino acids then pulls the ion pore open. And now we have sodium currents, which depolarizes. But they don't last forever. We also have an inactivation gate. So this is one big old polypeptide chain. So there are these loops that connect each of those 4 domains. And the loop connecting the 3rd and 4th is able to flop into the pore. So after we activate and open up the channel, there's a little bit of amino acid flopping around. And if it sticks in the pore, it stays there. And now we're inactivated. It doesn't matter that we're above threshold. No ions can move through because a little bit of protein flopped into the way. So we've blocked the pore. This is important because this is a positive feedback loop. We have to have some way of turning this off. If voltage-gated sodium channels keep driving their activation, what's going to stop this process? Just random chance. Eventually, there will be no more depolarization through voltage-gated sodium channels because they inactivate. So the action potential is only going to last 3 to 4 milliseconds. Not the rest of that neuron's miserable life, because it would eventually die from excitotoxicity. Maybe. It depends on the neuron. So we have strong depolarization, because it's a sodium channel, but transient depolarization, because it inactivates. And I've drawn a little cartoon there for you. So there's the cross-section through the membrane, and then below it kind of a top-down look, so you can see the little hole open up as you go from A to B. And then from B to C, that's that little bit of protein flopping in the way. That's our inactivation gate. So we have a look here. This is showing us membrane potential on top, the permeability or conductance of sodium and potassium, and then the currents that they generate. It's also showing you the activation and inactivation gates for sodium and potassium channels on the bottom. It's kind of a nice illustration. You should get what's going on in this. So where we're at right now is about the peak. We have sodium channels activated. Some of them are starting to inactivate. They won't deactivate and de-inactivate until we drop back below threshold. So sodium channels remain blocked until we close the pore. So we open up. After some period of time, the inactivation gate slaps closed, and it's going to stay there until we squeeze it out. Kind of like pinching an olive to shoot the pit out. So we have to close the pore in order to remove the inactivation gate. In order to close the pore, we have to go back below threshold. Now we would eventually drift there over time if we just inactivated our sodium channels, but we're going to get there even faster because of potassium channels. Now they're a little bit slower to open. They have about the same threshold potential as voltage-gated sodium channels. But our voltage-gated potassium channels are what we call delayed rectifiers. Delayed because they're a little slow. It takes them a little bit longer to open and also a little longer to close. And they're rectifiers because they fix the membrane potential. They put it back where it used to be. Okay, so these are pretty similar in structure, except it's not one string of amino acids. It's four. Four separate strings, so we don't have any loops inside that could flop in place. No inactivation gates. But the activation gate is still there. Same logic as the fourth transmembrane domain. It's positively charged amino acids. That's all the same. The fifth and sixth transmembrane domains still make up the ion pore. So it's pretty similar to voltage-gated sodium channels, just a little bit different. We use separate amino acids for each domain, so there's no inactivation gate. And we don't need it, because these delayed rectifiers create a negative feedback loop. Depolarization turns them on, but they don't cause depolarization. Instead, you could think of them as turning it off, but what really happens, they cause repolarization. This is a negative feedback loop. Depolarization activates them, and when they're activated, they cause repolarization. So they, by nature, turn themselves off because they use potassium, and potassium reverses at negative potentials, like negative 100 or so, but hyperpolarizing potentials. Now remember, they're delayed. So even though they drop below threshold potential, it takes a little bit longer to turn them off. And that's why, even after we're back at rest, our delayed rectifiers are still open. So we still have a higher potassium conductance than we had at rest. Thus, we hyperpolarize. We don't just go back to rest. We actually drop below resting membrane potential in the action potential. So let's walk through the whole thing again now that we got all that under our belt. So we'll call that, actually we'll do a solid line, why not? This will be 0 millivolts. We're looking at the membrane potential here. We'll put positive 30 up on top because I said that mattered. We'll put negative 70 millivolts here. Minus 55 for threshold. Something like that. And just for shits and giggles, we'll put a time scale on here. So this will be 1, 2, etc. milliseconds. So milliseconds on the X, millivolts on the Y. So we're a happy little neuron resting around minus 70. Let's say we get a little synaptic input and we hit threshold. Well, within about a second, we depolarize. So this right here, that's from synaptic input, except when it's not. But we'll just assume that it is for now. Synaptic input brings us to threshold. And then we're off to the races. At this point, voltage-gated sodium channels activate. So we move towards sodium's reversal. The next step is repolarization. So we'll come back down. And that's because of two things. Voltage-gated potassium channels activate and voltage-gated sodium channels inactivate. That's not the same thing as deactivating. They don't deactivate until we drop below threshold. Inactivating is blockage. Deactivating is closing the pore. De-inactivating, that's really a thing, is when we close the pore and then spit out that inactivation gate. And then the last thing that we got to consider, the after hyperpolarization. So we have going to threshold, dipole, repole, and after hyperpolarization. And this exists because voltage-gated potassium channels are slow. They're slow to turn on. That gives sodium time to depolarize us. They're slow to turn off. That creates the after hyperpolarization. So if you'll have a look on this graph here, look at the conductance. Sodium comes on earlier, potassium comes on a little bit later. It's the delayed rectifier. Now for many neurons, it's just all about sodium and potassium. Some mammalian neurons do things a little bit differently, but it's for the most part just sodium and potassium. And we know that because you can use drugs that target voltage-gated sodium channels, voltage-gated potassium channels, and you can completely screw up the action potential. Tetrodotoxin is an important drug here. Tetrodotoxin blocks voltage-gated sodium channels, so no more action potentials. Tetrodotoxin is a toxin found in pufferfish, although they don't make it. It's just the things that they eat make it, and they put it into their little quills or whatever you call their spines. Tetrodotoxin is lethal at a high enough dose because it blocks action potentials. So, no more respiration, no more heartbeat, and from there you can see life isn't going to last very long. I guess in low doses it tastes wonderful because people like to eat pufferfish with just a little bit of TTX just to get a taste of death, but not the actual experience. Tetraethylammonium is a voltage-gated sodium channel blocker, and you can see here in the little cartoon I've drawn for you, that kind of widens out the action potential. So it takes a little longer to repolarize because we've blocked our voltage-gated potassium channels. So, well, I guess I can draw it, why not? With TTX, we hit threshold, but nothing happens because we blocked our voltage-gated sodium channels. With tetraethylammonium, broader action potential, repolarization slower, no AHP, because tetraethylammonium blocks potassium channels. So we can see the effect of sodium and potassium here. Sodium causes the depolarization, potassium causes the rapid repolarization and the after hyperpolarization. Now, because of the nature of the voltage-gated sodium channels used, that causes our action potentials to be all or none. There's never a change in the height. We always approach sodium's reversal. So that's not the way that we encode how strong a stimulus is. If someone's lightly tapping you versus strongly tapping you, the difference isn't in the height of the action potential. It's in the frequency. So how quickly are we firing action potentials? That's what determines it. So the stronger the stimulus, the stronger this depolarization is. So if we have stronger synaptic input, it has nothing to do with this depolarization, only this initial portion. And if this is stronger, if we have continued strong synaptic input, then that's going to continue to depolarize us after we fire. We'll fire another action potential. Now, how quickly do we do that? It depends on how strong that depolarization is and how quickly we can hit threshold. Because remember, at the end of our action potential, we're hyperpolarized. So we're a little further from rest. We need stronger excitatory input to get back to it in this phase here. Right? Much further from threshold than we were at rest. And that's what makes the relative refractory period here. So it's relatively harder to fire another action potential during the AHP, during that hyperpolarization. So only strong inputs are going to do the job. We also have a limit on how quickly we can fire action potentials because voltage-gated sodium channels inactivate. We have to drop back below threshold so that we deactivate and then de-inactivate. If we don't allow a little bit of time for the de-inactivation, it doesn't matter if you open the pore, it's still blocked. So in the absolute refractory period, voltage-gated sodium channels are still inactivated, and that would be this time, right here. So here's our kind of absolute refractory period, and we'll draw it here. Absolute. When you're in the AHP and your sodium channels have de-inactivated, but we're further from rest because of our potassium channels being so slow, now we can fire another action potential. It's just relatively more difficult. Now that absolute refractory period not only kind of limits the rate of firing action potentials, it makes sure that these events stay as single events, propagating down the axon. We must, as a rule, bring the membrane potential back down below threshold before we can reactivate. All right, that's key here. All right, remember, after sodium channels open up, they inactivate, and only if they deactivate and close the pore can we remove the inactivation gate. So let's think about how charge moves down an axon here. I've color-coded the charge. Red meaning rest, right? Red is stop, and green is go. Green would be depolarized. So once we start the action potential there on top, so the gray neuron is just kind of showing you the schematic of the neuron, and then below that we're looking from early to later, okay, top to bottom. So the action potential starts at the initial segment and it moves in both directions. So it's going to move down to the next node. That node depolarizes, voltage-gated sodium channels open up at our second node there. So not the initial segment, one node down. Now that charge is going to move in both directions. Charge has no idea where to go, it moves randomly. The charge that moves down the axon encounters voltage-gated sodium channels that are not inactivated. So, bringing them to threshold opens them up, sodium can move, and we depolarize that next segment. But what about the charge that went backwards, back to the initial segment? Well, those voltage-gated sodium channels haven't deactivated and thus haven't de-inactivated. We're still repolarizing. So the charge that back propagates does nothing. There's nothing it can do. Those sodium channels are still inactivated. So we get what appears to be unidirectional movement of charge, even though it's really moving in both directions, which is kind of nice. So when you fire an action potential, it doesn't reverberate back and forth on the axon for the rest of that neuron's miserable life. No, it goes from the initial segment on down. Even though charge moves both directions, the back propagation of charge doesn't do anything because the sodium channels are inactivated. So the properties of sodium channels are pretty helpful in creating quick and single action potentials. Myelin is also helpful in speeding up the rate of action potential propagation. Now, not every neuron is going to conduct action potentials at the same rate. Neurons with larger diameters of their axon are going to conduct more rapidly, and neurons with myelination conduct more rapidly. So we have basically 4 groups. There's actually a little bit more than that, but we'll call them 4 groups of fibers. The largest fibers deal with movement. So they're either motor neurons or they innervate muscle spindles, so they help create stretch reflexes. But they deal with movement. Movement is the most important function of the nervous systems, and we want to make sure that we move now, not in a little bit. So we dedicate the largest myelinated fibers to movement. Now when it comes to sensation, I guess we can wait a little bit on that. So other than the sensing of muscle length, we need to know that right away, so that's group 1. Just knowing what's touching me. Do I have some vibration here? Is something moving on my skin? We use slightly smaller fibers, the group 2, or the A beta fibers, for touch sensation. Pain, we have a little bit slower. And there's 2 fibers that carry that. There's your group 3 and group 4, A delta and C fibers. C fibers are not myelinated, and as you'll see their conduction velocity is the slowest. These are responsible for that kind of long-lived but slow onset pain that occurs following an injury. So what's myelination doing for us? Well, it's affecting a few properties of the membrane. So it affects membrane capacitance. Right? So now maybe that time constant is going to mean something to you. We'll find out here. But what we got to think about is how far are we separating our charges? Right? Because the reason that the membrane is such an excellent capacitor is because it's so darn thin. So it's easy for charges to interact on both sides. So when we have our very thin lipid bilayer here, let's say this is our axon, right? Those charges can interact across both sides of the membrane. I kind of regret this. I'll just draw this side. There's plus up here. These charges can interact because the membrane's thin. Well, what if we were to take that membrane and instead of just leaving it naked there, we were to wrap it in several layers of myelin? Now the charges inside and out are separated by much greater distances. So the membrane capacitance drops dramatically. And I won't make you go back to lecture 3, I'm not a monster. The time constant's the product of membrane resistance and capacitance. If your capacitance drops to basically 0, your time constant drops to basically 0. So the rate at which the membrane potential changes in these myelinated regions is much faster. And that's going to help speed up the propagation of action potentials. I want you to think of the myelinated regions as essentially a slip and slide, or a well-lubricated section of the axon, so the charge just kind of slides along. It doesn't get trapped and stored like it does at the nodes. But we do want to trap it a little bit at the nodes because we want to activate our sodium channels there, and of course potassium as well. Right, because at the nodes we have ion channels. So we do want to give the charge a little bit of time to hang out at the membrane and stimulate our voltage-gated sodium channels and our voltage-gated potassium channels. And they're both at the nodes. Once we create that action potential at the node, we want it to very quickly move on down. So we don't care about storing it here. There's no ion channels. There's no reason to store the charge there. So it'll move along the inner node, the myelinated region, to reach the next node very, very quickly. Or you can think of this as a slide. And here's the ladder. You climb up the ladder, it's pretty slow, but once you get on the slide, it's quick. And it's passive. You let gravity do the work. However you want to think about it, you could also think of it like this. This is how I think about it. Or as a slip and slide. Those are fun. Now, not only do we affect the conduction velocity, increasing it about tenfold by dropping capacitance, we're also going to affect the metabolic load. In other words, how much ATP we have to spend per action potential. And we do that by increasing membrane resistance. Now you might think that these offset each other, but remember, if we drop capacitance to, basically 0, it doesn't matter what the membrane resistance is. We're not going to store that charge. But membrane resistance is kind of important to think about because the higher the resistance, the fewer the ions you move. And if you don't like to think about it in terms of formulas, that's fine. Just remember, there's no ion channels here. And these inner nodes are like 99% of the axon length. So the majority of the axon, if it's myelinated, doesn't have ion channels. So if we have, less than 1% of the axon that can move ions, that means we're spending, in an ideal world, 1% of ATP. This is a little bit of a lie here, but it's pretty good. We have about a 70-fold reduction in the amount of ATP we have to spend. That's pretty good, because remember, nothing's free. You always got to spend ATP, and making ATP, that has risks, just like everything in life. Every time you make ATP, you run the risk of creating free radicals, and, well, I don't want to take a journey to last semester, but we all know what happens if we make too many free radicals. The cell gets damaged non-specifically. So what's creating that ATP burden? I'm sure you're well ahead of me. The sodium-potassium ATPase. That action potential. Yeah, we're moving ions passively, but we got to pump them back. So, if we're bringing sodium in and letting potassium escape, we got to activate our sodium-potassium pump, or the sodium-potassium ATPase. Same thing. If we move less sodium and we move less potassium, we got to spend less ATP to drive that pump. Because we got to spend 1 ATP to send out 3 sodium and bring in 2 potassium, just like last lecture. So if we cut down on the movement of ions, cut down on ATP production, we cut down on metabolic stress. It's really nice. If you lose your myelin, you now have a heftier bill to pay. And this is why demyelinating diseases like multiple sclerosis can cause the loss of neurons, even though it's really a problem with the myelin. The myelin is so darn helpful, not just for speeding up action potential propagation, but for keeping our costs down. Alright, hopefully that made good sense to you, and if anything is tricky, fill out the questions box so we can talk about it in class. I'll see you later.